Good afternoon.
Good afternoon.
How are you all doing today?
Doing well. How about yourself?
Good.
I'm hanging in there. I don't know where you guys are all located, but it's snowing pretty hard where I am in Hillsdale. So I'm not super excited about that, but I guess that's what you get for living in the north. Anyone else buried in snow right now?
We got 5 to 6 inches of snow in Omaha.
Oh, lovely.
It's like
Yeah.
gonna be almost 60 today, so maybe it'll all melt.
Okay. Well, I'm hoping we'll get that warm weather to follow. It's a few inches right now. I'm not sure if we're going to get to 6, but all right. Well, let's go ahead and get started. We are on Power Series this week and transitioning towards Taylor Series next week, and that's the last big concept for the semester. So you can certainly answer any questions. If not, I can do an example or two. Let's start with questions. Anyone have something they're stuck on, whether from an exam or homework? Ben?
So I think I've started to get down the power series transformation, getting like when it asks you what the coefficient is for like C1, C2, C3. The only thing I keep getting wrong is, for some reason, my answer for C2 is actually supposed to be the answer for C3, and like my answer for C3 is actually the correct answer for C4. Does that make sense?
Yeah, so what problem are you thinking about in
So
particular?
I'm thinking of web work number 6, which is, right, 6x to the natural log of 1 plus x as a power series.
All right, so let me bring up WebWork on my screen so I can see what you're referencing. All right, you said it was from which set? 10.6?
Yes, this is 10.6, web work number 6.
All right, so represent this as a power series. And I guess I'll look at your version. Okay, so it asks you for C2, C3, C4, C5, and C6.
Mm-hmm.
And
Yes.
you're off by 1.
Yeah, like not like I'm off by like 1, like the value is off by 1, but that my answer for C2 is actually supposed to be the answer for C3.
Okay. All right, so why don't you walk us through how you went about finding this power series?
So I started off by taking the derivative of the original function we were given.
Okay.
So that gave me 6 over 1 plus x.
All right, so you take a derivative and you apply the, so I have 6x ln of 1 plus x. So are you ignoring the x for now?
Oh, sorry, my problem was, I think, 6x ln of 1 plus x, maybe?
Right.
Okay, so what?
See my screen right now?
Oh yeah, sorry, I see it now. So
Okay. But if
would
you
it
take
be
a
okay
derivative of that, what do you get?
Maybe I did, yeah, I get 6x, because I have to do the product rule.
Right.
Okay.
So I think what you were giving was the derivative of just 6 ln of 1 plus x, which is fine.
Yeah.
You can find the power series for 6 ln of 1 plus x.
Mm-hmm.
But then if you want to get the power series for 6x ln of 1 plus x, you need to multiply your answer by x, which is going to increase the power of x by 1, which would shift the coefficients by 1, which is probably what the issue that you're running into.
Oh, okay.
Okay? So the idea
Okay.
would be, once you can find a series for ln of 1 plus x, so maybe you find that this is equal to some sum of x to the n times cn.
Okay.
If you then want to have a series for 6x ln of 1 plus x, you would just multiply that by x,
Okay.
which would be the sum of cn times x to the n plus 1. But then the names of your cn's it really doesn't make sense to call them that. And so maybe we should call this, you could write this as a sum of x to the n with some other coefficient bn. And when it asks you for a constant, cn in this case, that's supposed to be the coefficient in front of the nth power of x. And so you're going to need to kind of shift your indices a little bit to get things to match up. So if it says C2, it wants to know what's in front of x squared when you write out your series. C3 is what's in front of x cubed, and so on. And since it's asking you for just a couple of them, you don't even necessarily need to find a general formula. You might just write out your series and then just find the x squared and x cubed and x fourth terms and so on.
Okay. I think I can try, I'll retry that by after doing the derivative, I guess, at the beginning correctly and see what I get. So.
So actually, I think if you take the derivative correctly, you're going to make the problem harder. So what my suggestion would be, it's okay to leave off the x and just find the Taylor series without the x, and then just adjust your series after the fact. That would be the easier way to approach the problem.
Okay, because I don't need to have the x in the derivative. I can just pull that out and then just do 6 ln of 1 plus x, and then at the very end, after I get my power series, just multiply that by x.
Right. If you know what ln of 1 plus x is as a series, it's very easy to find the series for x times the log.
Okay.
All right. Anyone else have a question they'd like to talk about? Nobody? All right. Well, should we do another power series example? Okay. Give me a minute here. I'm gonna come up with an example really quickly. All right, so this comes from chapter 10.6. I think it's number 14, if I remember correctly. And are you guys seeing the whiteboard?
Yes.
All right, awesome. So the question asks you to find a power series for 1 minus cosine of x over x. And so find the power series and the interval of convergence. So we want to find the series and figure out where this series actually converges. Now, if you've watched the videos for the next chapter, you'll know that there is a very systematic way that you can construct a power series for any function. And that is, involves using this formula that f of x can be written as the sum from n equals 0 to infinity of the nth derivative evaluated at some reference point times x minus that reference point to the n. So if you can find the pattern in the derivatives, you can always construct a power series. Now, for this function, we could apply that formula, but it is going to be a little bit annoying in the sense that computing derivatives of that is going to be a bit messy. We would need to use the quotient rule, and the derivatives get progressively messier the more times you apply the quotient rule. And so that's not going to be a great approach, although it would in principle work. In practice, it's going to be messy. So let's start with something that we do know. And in the videos and in the textbook, they actually give you the formula for the power series for cosine of x, which is derived using that formula. It is the following. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on, which can be written in the more concise way, the sum from n equals 0 to infinity of -1 to the n times x to the 2n all over 2n factorial. So the fact that we have two n's there just means that when n goes up by 1, our power and our factorial in the denominator both go up by 2. And so we're only going to include the even powers and the even factorials. Okay? So we can use that to construct this series for the function that we're actually interested in. And so let's start by looking at 1 minus the cosine of x. We'll notice that must be equal to 1 minus this sum, which would just be, well, the ones will cancel, and we'll be left with x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, and so on. And at that point, you'll notice this has the same terms as the original series. The only difference is we don't start with a constant, we start with the next term. And so we could write this with a sum starting with n equals 1. And then the other difference is that the signs have changed. So everything that was negative is now positive and vice versa. And so you can think of just multiplying by an extra factor of -1. And so I'm going to change the exponent of -1 to n plus 1. And I'll leave everything else the same. Okay, so we've got a series for 1 minus cosine of x now. Looks a lot like the series for cosine of x. And now if we want to find the series for 1 minus cosine of x over x, all that we need to do is divide that by x, or multiply by 1 over x. Which is going to be x over 2 factorial minus x cubed over 4 factorial plus x to the 6th over 6 factorial, x to the 5th. And in summation form, all that we did was we just decreased the powers of x by 1. And so there we go. There's our power series. We started with a series that we knew. We applied some basic algebra, some addition, subtraction, multiplication of powers of x, and that's just gives us a new power series. So that's the first part of the question. We now know how to find the power series. The next part asks us to figure out where that converges, and that's going to involve applying the ratio test to find the radius and interval, and then we'll need to check the endpoints to see if those should be included or not. All right, so let's look at applying the ratio test. The ratio of the n plus first term over the nth term would be given by, we'll have -1 to the n plus 1, so n plus 2, times x to the 2 times n plus 1 minus 1. Now, be careful there. You might be tempted to just increase the power by 1, but since n is multiplied by 2, the plus 1 should also be multiplied by 2. And then the denominator, same thing. There should be n plus 1 times 2 inside the factorial. And if you don't include those parentheses, it would be easy to get thrown off a little bit here. So those parentheses are really important when you're computing n plus 1. We're replacing each n with an n plus 1. And so whatever is multiplied by that n is multiplied by the entirety of the n plus 1. All right, so that's the n plus 1 part. We need to divide by an. And so that will just be the same as multiplying by the reciprocal of an. And before we can simplify that, let's notice a couple of things. x to the 2n plus 1 minus 1 is the same as x to the 2n plus 2 minus 1, which is the same as x to the 2n minus 1 times x squared. It's because it's just got 2 extra powers of x. And similarly, 2 times n plus 1 factorial is 2n plus 2 factorial, which is just 2n plus 2 times 2n plus 1 times 2n factorial. And so with that in mind, if I want to cancel out the powers of x, we'll see that I have an extra x squared in the numerator. And if I want to factor out or cancel out the factorials, I'll be left with a product of 2n plus 2 and 2n plus 1 in the denominator. And of course, when we take absolute values, it really doesn't matter how many negative ones we have, because that's ultimately just going to become a positive one. And so we'll be left with the limit as n goes to infinity of, in the numerator, we just have an x squared. And in the denominator, we have 2n plus 2 times 2n plus 1. And here I've dropped the absolute values because everything is positive. And that limit is not so bad because the numerator is not changing and the denominator is getting larger. And therefore, this must be approaching 0, which is always less than 1. And so that means that it doesn't matter what the value of x is, we're always going to converge. So the radius, we would say, is infinite, and the interval is just negative infinity to infinity. Okay, any questions about that one? Okay, well, in terms of power series, what you need to be able to do is you need to be able to construct a power series. That means either relating the function that you're trying to describe to a geometric series or some other known series, and then by recognizing the steps needed to connect those two things, manipulating one series to turn it into another. Or, as you see in chapter 10.7, applying Taylor's formula for finding the power series. And then you also need to be able to find where those series converge. And so that means looking for the radius or the interval of convergence and applying your other series tests. So these types of problems really kind of bring all of the concepts from the entire unit together. You'll find that the endpoints often involve alternating series. At least one endpoint often does. The other often is a non-alternating series. So you may need to use your alternating series test, and you may need to use some other convergence test for the endpoints. You need to use the ratio test usually to find the radius of convergence in the first place. And often geometric and telescoping series can show up here as well. So there's a really wide variety of different techniques from this chapter that come into play in these power series problems. So would you guys like to do one more, or should we call it a morning?
I'm down for one more.
Yeah, that would be good.
All right. Let's do one that's backwards. Okay, let's do one where we have the sum, and we'd like to figure out what it converges to, but still using all these concepts of power series. So let's look at the sum of, how about, let's do negative 3x to the n over 2 to the n plus 1. Okay, so that's a power series. And we'll say we're start at n equals 0 to infinity. And let's find the radius and interval of convergence and figure out what it converges to. So it's backwards from the previous one where I gave you the function and said find the power series. Here I've given you the power series and find the function. All right, so in terms of radius and interval of convergence, we can again apply the ratio test. So we'll have negative 3x to the n plus 1 over 2 to the n plus 1 plus 1. Okay, so simplification here. It looks like we have one extra factor of 2 in the denominator, and we have one extra factor of negative 3x in the numerator. And so we'll have the limit as n goes to infinity of negative 3x over 2. Well, that doesn't have any n's left over, so the limit is just negative 3x over 2. And this is going to converge as long as that quantity is less than 1. So we could say that, well, 3x is less than 2, or x is less than 2/3. Okay, so there's our radius of convergence. And our interval of convergence would therefore be x is going to be between 2/3 and negative 2/3. And the question is, should I include those endpoints or not? And so let's check them one by one. We had the sum from n equals 0 to infinity of negative 3 times x to the n over 2 to the n plus 1. Let's check when x equals 2/3 first. If we plug that in, we'll have the sum from n equals 0 to infinity. In the parentheses, we'll now have a negative 2. And notice that is really just the same as negative 1 to the n times 2 to the n over 2 to the n plus 1, which simplifies down to the sum of negative 1 to the n over 2. Well, what do those terms look like? Well, the first term is going to be a negative 1 to the 0, which is a plus 1 over 2. The next term will be a negative 1 to the 1, so it'll be a negative 1/2. And then we'll have plus 1/2, minus 1/2, and so on. And you can see that the terms are not getting smaller, and so this one is divergent. And so that means that our greater than sign there is correct. We should not include 2/3 as part of our interval of convergence. All right, let's check our other endpoint. We'll have the sum from n equals 0 to infinity. If we plug in negative 2/3, we're now going to have just a 2 to the n in the numerator, which means our sum is just 1/2. Add it up over and over again. Well, by the same line of reasoning, that one has to diverge as well. So our other term, our other sign is correct as well. We don't need to include negative 2/3 either. Are you with me so far? Okay. All right, so on to the last question. What does this converge to? And we will not be able to answer these sorts of questions all of the time, but we can for cases where it's related to unknown series. And so let's try to manipulate this expression a little bit to make it more like a series that we recognize. So the first thing that I'm going to do is I'm going to write it as with an nth power. So we have a negative 3x to the n in the denominator. We can write that as 2 to the n times 2. And in fact, if we wanted to, we could pull that factor of 2 right outside and just have 1/2 times the sum from n equals 0 to infinity of negative 3x to the n over 2 to the n. Or we could just think of that as negative 3x over 2 to the n. Okay? So we just did a little algebra to rewrite it. And notice this looks like a geometric series, where the r is equal to negative 3x over 2. And if we wanted to put the 1/2 inside, well, then we'd say that the c is just 1/2. And we know what geometric series converge to. They converge to just c over 1 minus r, which would be equal to 1/2 over 1 plus 3x over 2, which you could simplify to, if we multiply by 2 in top and bottom, it would be 1 over 2 plus 3x. And so there we go. We know that our power series is just a power series for the function 1 over 2 plus 3x. And we can check this. So our series was the sum of negative 3x to the n over 2 to the n plus 1. And so let's graph that. And then I'll graph the function that we think it converges to. Is 1 over 2 plus 3x. And we'll see that it does look like they match up over some range of x values. It's, well, I'll throw this out to you all. Where do you think the green and the red match up?
From negative 2/3 to 2/3.
That's what one would hope, right? Because that's the interval of convergence that we found. And there we go. I just added x equals negative 2/3, and it does look like that's the asymptote where they break down. And if we add x equals 2/3, that does seem to be the other point where things start to break down. So there we go. We're on the right track. Okay, so we can relate power series to the functions that they converge to in both directions. We can find the series from the function, and we can find the function from the series if we can, again, relate it to something known like the geometric series. Any other questions?
I don't have any.
Okay. Well, if you're all set, then we'll end here. Monday will be the next chance to knock out some objectives. And then I think I have one more chance on Friday before the final exam. So I will plan on having office hours on Wednesday of next week. And then on Monday of the following week, since those are not exam days. And I'll also be available for appointments if you have questions in the meantime. But we won't have our regular office hours on those other days since you'll be busy with the exam, presumably.
Is objective 12 going to be available Monday?
It will be available Monday if you're working ahead, yes.
Okay.
So we're gonna have 2 exams next week too, Monday and Friday, and then also the final.
Right, so there you have 3
Alright.
more chances basically to knock out objectives. And you don't have to do all of them. I'm just trying to give people as many chances as possible so that you
Yep.
can do as well as you can.
All right, thank you.
All right, anything else? All right, if not, have a great afternoon.
Thank you, Dr. P.
Yep, take care.